are usually clear inside. But Barakat and others have found samples where some of the quartz grains have distinctive lines caused by shock waves from an impact. This seems to provide more support for a meteorite impact here in the Sahara Desert. But it doesn't explain why the glass is so different from other meteoritic glass. The team can't agree about the significance of this evidence.
I'm really interested in the distribution of the shocked quartz relative to the glass.
Right.
Seems like the glass covers an area of hundreds of square kilometers, but it seems like the observation of shocked quartz is only in one spot.
Right, yeah. Well, I'm not sure that we know for sure yet where the shocked quartz is. There are a few spots that have been surveyed so far and needs to be confirmed. Do you see any glass?
But Kerbel thinks he has made a discovery, which leaves no doubt as to the origin of the glass.
I think this sandstone is broken up.
Most of the glass is completely clear, but a few pieces are not.
There's a nice little piece.
The ones that show clear, white, and black, all in one piece.
Yeah.
The pieces of glass with black streaks of material inside are key to Kerbel's discovery. To establish what the material trapped in the glass was made of, Kerbel examined it in his lab in Vienna. He analyzed it by bombarding the black bits of the glass with neutrons, and after weeks of measurements found small traces of the exotic element iridium.
Here are the peaks that indicate the presence of the element iridium, and this is something we would not expect to find in rocks on the surface of the Earth, and this is characteristic for meteorites. So here we have very good evidence that a meteorite really hit the Earth and was incorporated with the glass when it formed.
Finding iridium is good, but not conclusive evidence of a meteorite impact. After over a year of searching, Kerbel found another rare element, osmium.
The results are absolutely exciting. We see that the abundance of the element osmium is about 50 to 100 times higher than what we would ever find on the surface of the Earth. And more importantly, the ratios of the isotopes of osmium are very different from surface rocks of the Earth. They are clearly extraterrestrial and show that a meteorite hit the surface of the Earth and the sand when the desert glass formed. So we have a eureka moment here. We now know there was a meteorite impact.
Kerbel is now totally convinced that a meteorite was involved in forming the glass. But there was an obvious problem with the meteorite theory. Perhaps the biggest problem of all. A meteorite impact leaves behind a crater. And no one has ever found any trace of a crater in the area where the glass is found. For Kerbel, the lack of a crater doesn't create a problem. He has an easy answer.
I think what we're looking at is probably a very deeply eroded structure. A fresh young crater looks maybe like this, and it is filled in here with broken bits of rock and melt and so on. But with time, all this disappears, and all that we might have left is this central area here, which is very difficult to detect.
A meteorite large enough to scorch and melt such a vast area of ground had to be big. And even if the crater's been eroded, there is still one place from where it should be possible to spot it.
Booster ignition and liftoff.
Farouk Elbaz is head of the lab in Boston that interprets pictures of Earth taken by orbiting satellites. He's been looking at pictures from space since the 1960s. Back then, only about 20 impact craters had been found.
With the advent of satellite images from space and the fact that we're going to be recognizing all of these circular features, we now have at least 200 that are proven or semi-proven impact craters.
One reason there are not more known impact craters on Earth is that some are so big they can only be spotted from space. And the older they are, the harder they are to find.
It is really important to look for a crater that has the right age for the formation of this class, because if we say that this class is of meteorite origin, which is most likely, then there should be a crater of that age that would have formed that glass. So these things must come together.
To help Elbaz in his search, he needs to know the age when the glass was formed. And it is possible to pinpoint the age. One technique is based on the rate at which the element uranium decays. It leaves tiny scratch marks on the glass, which, when counted, gives its age. This method produced a date for the desert glass. It was formed nearly 30 million years ago. It was an important result. But could they find a 30-million-year-old crater?
It's not really a problem in this part of the world to locate a 20 to 30 million year old structure, because no matter what the erosive processes were like, you still have in the subsurface the imprint of that impact. For instance, we have the structure here in Chad that has been dated to be older than 200 million years, which means that anything that is 20 or 30 million years would certainly be visible.
So Elbaz and his team have been searching the area looking for suitable candidates.
We have some craters in here, a tiny one in here, larger craters in south of here, but nothing in that zone that can be called an impact crater. So here is the Great Sand Sea and the dunes going down southward this way. And the silica glass region is right here, and it is a little too far from any of the impact craters that we have formed around. So we conclude from that we have not really found the smoking gun for the silica glass in the Western Desert in Egypt.
Whilst studying the satellite images, Elbaz spotted a circular formation that he thinks needs closer inspection. But the formation is 100 kilometers from the main concentration of glass, and other scientists remain doubtful that this could be the source. Yet, if there's no crater, then some enormously powerful cosmic event happened here nearly 30 million years ago, and left little more than glass behind. It's this seemingly impossible puzzle which could be solved by the new theory Mark Boslow is developing. The theory starts with an observation made 60 years ago in the desert of New Mexico. The Trinity site is where the world's first atomic bomb was detonated. Sergeant Ben Benjamin was part of the official photographic team. He was just 22. Cameras were set up at several locations. Ben Benjamin was in a concrete bunker 6 miles from the blast site. For all of them, it was an awesome, almost surreal experience. At 5:29 on the morning of July the 16th, 1945, the bomb was exploded.
We had a PA system. They were counting down in seconds, and when it came to -10, I switched on all 4 cameras, and it went off, and it was incredibly bright. It turned out to be 20-some times the brightness of noonday sun. And my God, it was the most amazing thing that I had ever seen in my life, and I'll never forget it.